Hi everyone, Abby and Emmanuel here, and today we'll be discussing our approach to optimizing video call experiences through direction of voice-based noise filtration. The motivation for this work relies heavily on the transition towards integrated work-home contexts and the increased significance of video calling during current times. Often, multiple verbal interactions may occur during a video call within a single room, some of which may not be intended for the call participants. Consider this scenario. You're in the middle of a presentation and your family member asks you a question without realizing that you're in the middle of a call. You turn your shoulders and let them know that you're busy. Ideally, this brief interaction wouldn't be picked up and conveyed to the rest of your colleagues. Generally, conversation that is intended for the call participants is directed towards them. For that reason, we thought it would be interesting to be able to filter the audio that is processed from an environment to video call participants depending on the direction of voice. Before we move forward, it's important to understand the difference between direction of arrival and direction of voice. Direction of arrival refers to the relative direction of the sound emitting source from the sound receiver, to illustrate where the speaker is relative to the microphone. In contrast, the direction of voice is the projected axis along which the sound is emitted. For example, if the speaker was speaking directly to the microphone, or if the speech was projected plus or minus 45 degrees from the axis between the person and the microphone. Our work takes inspiration from the direction of voice estimation for intuitive speech interaction with smart device ecosystems paper published in UIST 2020. Along with their method, they've released a publicly available dataset which contains approximately 11.5K recordings from 10 participants saying, "Hey assistant," and the quick brown fox jumped over the lazy sheep at 8 angles with 45 degrees increments from 0 degrees to 360 degrees in 2-room setups from 9 different positions. These recordings were recorded by a ReSpeaker USB 4-channel microphone, which we've purchased for some experimentation. The methods described in this paper are an insanely effective example of how good featureization and simple machine learning methods can accomplish a goal. Our approach consists of a featureization task for pre-processing the audio segments. The generalized cross-correlation phase transform, or GCC FAT, of each of the combinations of the 4 channels of the ReSpeaker microphone were taken, which resulted in 6 GCC FAT correlations. This was cropped by the maximum theoretical delay due to the distance between the orthogonal microphones around the max peak. With this raw output, the value of the max peak of each of the correlations, the delay between the channels, and the area under the curve of the GCC FAT were used. The standard deviation, mean, and range of the GCC FAT correlations were also used as features. These features were fed into an extra trees classifier with 1,000 estimators. We trained 2 models, one for discerning whether the subject was facing or not facing the microphone with a plus or minus 45 degrees threshold, and another model to discern a plus or minus 90 degree threshold. The filter would sample user-defined time lengths of speech segments and let audio segments through if it were classified as a facing speech segment. Handing windows were applied to the audio so that audio segmentation could occur before featureization. The paper tests out the robustness of their method with a few different test splits, but we decided to design our own test split to be more representative of our use case. Our training data consisted of all voice segments from 8 participants in 1 room. The test set consisted of held out voice segments from 2 participants across all other parameters in the held out room. The purpose of this test train split is to achieve cross-speaker and cross-room robustness. Since video calls may be conducted in rooms with drastically different reverberation properties and must be robust enough to handle new speakers, we hope that this test train split will be representative and capable of generalizing along these axes. For the filtration task, we use the test data to curate audio segments where facing and not facing audio segments from the 2 speakers were both present in individual audio clips.
So even with our new train test split, we were able to achieve pretty good test accuracy. I'll actually switch over to the notebook right away. We can see that in our test accuracy for the 90 degrees to minus 90 to 90 degree model, we were able to achieve about 84% test accuracy. Um, Whereas in the minus 45 to 45 degree model, we were able to achieve a test accuracy of about 90.6, maybe round up to 91%. Um, this is the demo of what we've been able to accomplish so far. So I actually went and got one of these 4 mic arrays that was used in the original paper. It's a little tiny circuit board thing that allows you to record 4-channel audio. Nothing much to it. And yeah, so I'll just here and just play one of the clips that I recorded. What's up, gamers? Thanks for tuning into the stream. I'd like to thank everybody for the 500 subs. Wait. I'm recording. Oh my god, wait. What's up, gamers? Thanks for tuning into the stream. You can see that there are like multiple audio clips. In Audacity, they actually look slightly different. Here's actually another clip that I recorded, and you can see that if you inspect it, like I don't know if you can really see it, but um, you can see that like there's like slight deviation in the just because the microphones are just slightly apart from each other. So anyway, I have a script here that just takes in all of these audio files, and takes in all of these audio files and runs them through our classifier model in segments, and then outputs the segments to a new audio file if they pass, um, and if they don't, it just outputs a bunch of zeros into it. So I'll just go ahead and run one of them. I have to run Python 3.7. Never mind my dependencies. Okay. Um, filtering.py, um, and I input the file prefix, and I actually have to specify a window size. Um, so this is one of the parameters that I think we need to investigate a lot more of, like quantitatively and stuff, because definitely like different window functions and Han windows and the size of the window might have an effect on the thing. So I'll just go with about 800 milliseconds. So the original paper went and actually just did it on whole audio clips, and so we're thinking that something close to 1 second will probably work well enough. And then I'll just specify the output demo. So it takes a while to pre-process, and then I actually so this segment X facing, this is just this is the actual time in seconds, and these outputted numbers right here are just the time it takes to process each window. I've seen like throughout the experiments that it's pretty constant at around 700 milliseconds here. So yeah, we'll probably have to take that into account as we continue on, like trying to eventually work towards the goal of being able to let this classifier run live on a live audio stream. So I'll just go ahead and play. Um, so it outputs 4 audio files back. I'm just going to play the first one, and we'll just see how it sounds. To the stream, I'd like to thank everybody for the five. I'll start that over again. To the stream, I'd like to thank everybody for the 500 subs. So that's kind of interesting because you see that there was a couple of false negatives at the beginning. I think part of the reason for that might be because I was like sort of shouting at the beginning with my little hype intro and whatever. But and that might actually mess things up a little bit, and I don't exactly know why. But we can see that it was at least able to like completely take away the backwards facing audio, which I think was really good. For future directions, we are thinking about possibly using the diffusion masks as we have talked about in our paper presentation from the research from Lee and the company to try to get higher quality features to filter out noise. Also, definitely a big one that we've seen in the demo, examining the effect of the window size on the quality of the predictions and what other effects it might have about the model in general. And also try to improve the performance, 700 milliseconds per segment as we've seen so far. It still needs to be investigated, and then we need to improve it in order to work towards the goal of the model being used live in a live audio feed of maybe a stream or a conference call kind of setting. Thanks for listening.